Hey data junkies, welcome back. We're jumping right back into our one-way ANOVA, analysis of variance, and in our earlier videos we set the foundations, showed you the math, showed you how to calculate it by hand working on a survey with the Munchkins out in the Wizard of Oz land. And so now we're going to take and continue this a little bit more and talk about the different assumptions. I gave you a brief introduction to the assumptions you need to know, but here's where we're going to start testing them and seeing what some of our thresholds and limits are. So in this case, we're going to really focus on normality and variation, but we're going to talk about the others as well. So the major ones that we're going to need to be concerned about, I just mentioned, are normality and equal variance, which is called the homogeneity of variance. We also are concerned about independence. You have to make sure you have independent data. The other ones we need to be concerned about is what does our dependent variable look like? Do we have equal sample size? And these affect the other aspects as well. So everything kind of goes hand in hand. Now I'm going to introduce a couple new terms into my videos here called pre-test and post-test. These aren't any sort of statistical tests in and of themselves. It's just a frame of reference of when can you check some of these assumptions. Some of them you could check before we run the ANOVA. Some of them we can check after we run the ANOVA. So all of them we're going to be able to check with the one-way ANOVA as a pre-test, with the exception of normality. And I'll show you why when we get to that one. But as we move towards regression, you're going to hear me using more often these terms of sort of a pre-test and post-test approach with our checking assumptions. So the first one is independent observations. And so in order to get this one out, there's nothing we do in R specifically that says that you're going to have independence. This is good old-fashioned roll up the sleeves, hit the pay dirt, and get to know your data. Know where it came from. Know who put it together. Get some history on it. If you collected it yourself, even better. You'll know it better than anybody else. So in this case, you have to understand the study design. You have to know how is it put together, what sort of biases might there be, what sort of limitations might there be, what sort of influences might the data have with each other, and that's where you really get that understanding of the independent data. Of course, if it's randomly selected, closer towards experimental designs, these are more secure, more favorable of the different approaches that we can get. And you have to be careful of things that can creep in that are dependent data. Things like if you're comparing two exams in a particular semester, a midterm and a final. The results for the final are going to be somewhat influenced by how well you do on a midterm. Whether you do well, whether you don't do well, there is a relationship between them. And so another thing you might want to look at is, oh, well, exams, of course it's easy. Well, how about something that's not as specifically time dependent, but still has dependency to it? Think about somebody who has home ownership, and they're getting different lines of credit cards. And both of them are coming in because of that particular home ownership. And so there's a dependency there between having that status of the home and having multiple offers at the same time that are going on. Now, the other one that we're talking about is having a numeric dependent variable here. So in this case, it has to be integral or ratio. It's okay to have ordinals with 5 or more categories and no extreme outliers. If you have extreme outliers, then typically we have 2 strategies that we can use. We can drop the offending values, or we can Winsorize them. Winsorize them is a fancy stats term for saying we're going to use a trim on the data. We talked about trimming earlier when we did our descriptive statistics, and that's where you just sort of take a little bit off the very top and very bottom, sort of trim off the edges, if you will, and it drops those data points on both sides to give you a bit more of a balanced dropping effect from your particular data here. You could also keep it in depending on the extent of how much of it's an outlier, but just keep in mind that it is going to affect your analysis to one way or another. And dropping observations is contextual based on the situations that you're in. Sample size is very important here, as it's going to influence much of what it comes next. And as long as you have equal sample sizes, that's going to build in and pad you with some protection against the variations that you might be experiencing with variance and normality. So the more you violate those assumptions, the less you have to worry about it if you have equal sample sizes. When you have unequal sample sizes, some things can start to creep in. So first of all, it can give you a problem with your grand mean. You're going to have overrepresentation in some groups relative to others, and it's going to swing the grand mean in their favor. You could have homogeneity of variance issues. So the more data points you have in a particular group, the broader it can swing its variation relative to others. We can take care of it with weighted versions of the ANOVA. We're not going to go into the mathematics of how that works in this particular course, but it is out there. And one of those methods is what we call the Welsh ANOVA. And so the Welsh ANOVA helps compensate by having these unequal variances and unequal sample size groups, or we can swing it into the non-parametric version we're going to talk about later called the Kruskal-Wallis, and that'll help with the sample sizes part when we get to normality problems. And so also keep in mind that when we're doing power analysis with ANOVA, that we have an n, which is the sample size for each group, but we only get to put in one n, and we put in the smallest size of the sample group. So the smaller n you get to put in your power analysis, it's going to affect your power coming out the other end, or any of the other metrics that we're using to determine. And so keep in mind that this has a different effect as well. As we go into other types of ANOVA, it's going to play with how it works in those cases differently as well. So let's move on to normality. Normality is talking about the model's residuals that should be normally distributed. Well, wait a minute here. Residuals? What's that? We haven't really talked about residuals in this class yet, so let's go ahead and take a brief moment to introduce the concept of a residual. So a residual is just a fancy stats word of talking about the error, the stuff we don't know, the unpredictedness. And so we have some average amount. This average amount happens to be a predicted value that the ANOVA can generate, and we're seeing each observation point that we have, how far is it from that average fittedness? And that distance that between what we have and what we could predict is our residual. And so we're saying the error, that unknown stuff that's going on there, those distances, that when we bring them all together, we can distribute them out. They should be normally distributed. So now that we've got our residuals down, let's go ahead and just move forward a little bit. So I'm just going to do a brief couple of snapshots here with some toy data I put together. We have some sidekicks from fiction here. All of them happen to start with the letter S. And I had 80 people split into 4 groups of 20 each, and they rated each a particular sidekick on a scale of 1 to 100 on how awesome that sidekick is. So let's use that as our line here as we're looking at some of this. So when we're checking for normality, we're going to use what's called a QQ plot. And we've talked about QQ plots before. It stands for quantile plots. And what you're looking to see is we're using the residuals in this case. We're doing the QQ plot on the residuals. And what we should see is that the dots form a sort of 45-degree line from the bottom left towards the upper right. And we're going to cut a line through it, a QQ line. And those data points should hug the line pretty closely as it goes from the corner to corner. The closer to the line, the more it's hugging it, the more it's on track, the more normal we are. That the values we should theoretically find are being found where we actually have them. And I could then show you one that doesn't look so normal. So we can see in this particular case that our different data points here are swinging away from the line. This is typically seen within a large amount of skew. And I have put down in the bottom of the graphic here for you just a histogram of the residuals for you as well. So what we can see when the non-normalness that we have, there's a long tail going out to the left and a tall spike on the right. Now, when we have a warning about normality, depending on the stats books you're reading and the internet pages you're coming across, you may hear about different computational tests. Looking at the QQ plot is sort of an eyeball check. It's a rough metric where we kind of look at it, see how it's tracking against the line, and you're going to have to look at these things over and over to get this sort of gut intuition about when it's normal and when it's not. And you'll start to recognize these. So you might, in the meantime, want to go check out a more computational approach. You may hear of things called the Shapiro-Wilk test or the Kolmogorov-Smirnov test or KS test. And these are great for helping determine if a variable is normally distributed. But in this case, we're looking at the residuals. And this can be a little bit more sensitive than what these tests can be picking up here. So in this case, the QQ plot is going to be your best approach for what we're looking at here. Don't use the Shapiro-Wilk or the Kolmogorov-Smirnov. And so you may also recall that I called this a post hoc test, because we're going to come back to this one here, but in order to get the residuals, we have to actually conduct the ANOVA first. So moving on, we have the homogeneity of variance. The homogeneity of variance is our equal variance one. This is saying we have all of our different groups, and they should be somewhat similar to each other when it comes to their measures of dispersion. This is their standard deviations and their variance. And so a good way to crank this out visually, just a quick estimate to see where they're looking at, generate some box plots. You've got one box plot for every category that you have, and it's against a numeric DV, so it goes very well to generate out a box plot. And when you're looking at these, look at the size of the boxes, look at the lengths of the whiskers, compare them across the groups. Now, it doesn't matter so much if one box plot is much higher or lower than others, or they're moving together in trends. What makes a difference is the size of the box and the size of the whisker. That's talking about how much dispersion do you have within that particular group. And so the more similar they are to each other, the more they have equal variance. And in this particular case here, we have 4 box plots in gray, green, red, and blue, and they're all pretty well approximate to each other. Contrast this with this next one, where we have different box plots. Some of them are very thin, some of them are much larger, and some of the whiskers are also very short, some of them are very long. And so as we get these box plots that are differentiating from the others in the pack, then we're going to start to come out and say that they have unequal variance here. So in this case, it looks like Samuel Tarley has the perhaps most awesome ratings, but also has the largest variation, where somebody like Spock has much more of a tighter variation with a higher up score. So just keep in mind when you're charting out these different variations here that some of these curves and these plots can come in different shapes and different sizes, and you'll start to look at these things a little bit more and more, and you'll get a feel for them as we go. But feel free to always check with me if you've got a question on how something should look. Now, as we still talk about this homogeneity of variance, I gave you an eyeball method before, but we also have a numeric way to check this out, a computational approach. Now, when you worked with the t-tests, you had the equal variance test, the var dot test that you did. And in the ANOVA land, we have something similar as well. We had the Levene's test. The Levene's test, like the variance test that comes before it, has its own null and alternative hypothesis. The null says that the variances are equal. The alternative says that at least one variance is not equal. So it follows very much in the flavor of the ANOVA's hypothesis, but in this case it's talking about specifically about variance, not about the means. It uses a p-value, and so if the p-value is less than the alpha you've set for the rest of your analysis, which in my case happens to be 0.05, then you go ahead and reject the null and say that you do not have equal variances. If your p-value is larger than the alpha, then you fail to reject the null and your variations are close enough to each other to say that they're approximate. So we use that to help us get a conclusion out of this particular test here. And so this is a post-test approach. We can test this before we do the ANOVAs. The Levene test, it's in the CAR library. It uses the means. There's a quick option we can tweak on there, and we have a Brown-Forsyth test. Don't worry about the name so much, but just keep in mind that this version uses the median instead of the mean, and otherwise it keeps a similar type approach. So when we're going to put this into R, we use the CAR library. The function is called Levene test with a lowercase l and an uppercase t. Keep that in mind. And then you're going to put the variables in d tilde iv just like you would when you're putting it into your ANOVA, which we're going to get to in the next videos coming up. And now keep in mind the default setting. If you just do Levene test dv tilde iv, it's going to give you the median by default, which is going to give you the Brown-Forsyth version. If you want the mean, you have to put comma, center equals mean, and it'll generate the test of variance for you using the Levene's test. Now, the median version is actually more robust than the mean, which is usually the reason by its default, but it has higher standards, meaning you need a larger sample size in order for it to work properly. For most of us, that's not going to be a problem here. But if you're dealing with smaller groups, like let's say the Munchkin group, where I only had 5 in each group, that's not going to cut it. Normally you're going to need somewhere between 10 to 15, maybe upwards of 20 in each group in order to be able to use the Brown-Forsyth test well. So just keep in mind then that these are the different assumptions we're going to have, and if you start violating some of the assumptions, what do we need to worry about? Well, I said before, as long as your sample sizes are relatively equal to each other, and they're also a little large being larger than 30 in total, then you're good for a lot of the things that are dealing with normality and variance issues. Those will water themselves out. It becomes a bit more of a problem when you've got small samples and when your samples are of unequal sizes. Now, when you meet some of these precautions, you're going to have one of two strategies that you can look towards. We can use what's called the Welsh ANOVA, or we can go with the non-parametric version called the Kruskal-Wallis. And I'll be covering those in the upcoming videos. I'll see you then.